Hi, everyone. I want to first thank the organizers for giving me the opportunity to talk here. And I'll be talking about some work that we recently did. This is with Kai-Min Chung, Xiaodi Wu. And this is about another kind of parallel repetition. We've heard from Ankit a result about classical parallel repetition, and from Thomas about non-signaling parallel repetition. This is about the quantum version. And this uses some what I think is some interesting ideas from communication complexity that I think is new. So let me briefly go over the setting again. So we start with a two-player one-round game. So you have a referee, and the referee will choose questions from some distribution mu and send them to these two players, Alice and Bob, who can't communicate. And the players respond with answers A and B, and they win the game if X, Y, A, B satisfies some predicate V. Okay. And how did the players produce their answers? Well, they use some strategy. And most generally, we can think of a strategy as just being some conditional probability distribution. For a given input X, Y, there's some distribution over A and B. And if you're given a strategy S, then you can measure how well they do with this strategy. So we call this the value of the strategy. And basically you say, well, over the choice of questions from mu, how often can they produce winning answers? So, given a game G, what is the best that Alice and Bob can do? So it depends on what kind of strategies you talk about. So if you think about deterministic strategies or classical strategies, then the best, the maximum probability they can win is called the classical value. And this is where you maximize over all strategies where, Alice's answer is a fixed function of her input, her question. And Bob similarly answers a fixed function of his input. Okay? This is the classical value. But we can allow Alice and Bob to employ more powerful strategies. So imagine that they use something called quantum entanglement. And it's not important to know what exactly this is, but think of Alice as possessing some particle and Bob possessing some particle. And these two particles are correlated in very special ways, dictated by the laws of quantum mechanics. And quantum entanglement, if they use this, allows them to produce correlations that outperform any classical strategy. And when you consider quantum strategies, we can measure, well, the maximum winning probability they have is what we call the entangled value of a game. Okay. And what's the relationship between these two values, the classical and the entangled value? Well, we know that the classical value is at most the quantum value. You can do at least as well if you're allowed quantum strategies. But we know of games where there actually is a separation. So for example, this CHSH game, classically, you can do no better than winning 3/4 of the time. But if Alice and Bob share quantum entanglement, they can produce answers that win about 85% of the time. So quantum strategies are more powerful. Okay, so let's talk about the parallel repetition of a game. If you start with a game G, you can repeat it in this very natural way to try to make it harder. So the referee will choose n independent question pairs from the original distribution and send them to Alice and Bob simultaneously. And they have to produce n answers all at the same time, and they win this repeated game if they win each of the individual games. Okay, so we've seen this before. And then the fundamental question about parallel repetition is, well, how does the value of this repeated game compare, behave as a function of the original game value and the number of repetitions you take? So we know of counterexamples that it doesn't behave as nicely as we would want it to. So we know of games, for example, G, its value is 1/2. But if you repeat it twice, the maximum winning probability is still 1/2. So it's not true that the value of G, this repeated game, is the original value raised to the nth power. It's more complicated than that, but we still have an exponential decay. And this is known as the parallel repetition theorem. It's first proved by Ron Raz, simplified by Thomas Hohenstein, and extended by Mark and Ankit recently. And the value of this repeated game, the classical value, is upper bounded by some complicated function of the output alphabet size and epsilon, where the original value of the game is 1 minus epsilon. Okay, but the important thing is that the value of this repeated game still goes down exponentially with the number of repetitions. Okay, but we're talking about quantum games, so we can ask the same question about the entangled value. So if you do this parallel repetition of g, how does the entangled value of g to the n behave as a function of the original entangled value? The question is, does the repeated entangled value also decay exponentially in n, or does it decay at all? And for general games g, this is not known, surprisingly. But we do know some things, and in the past couple of years, there have been some partial results. And I just want to highlight, last year, the most relevant to this talk, we do have parallel repetition theorems for entangled games, but for special classes of games. And those two special classes are what are called free games. So these are games where the questions to Alice and Bob are independent. Okay, so mu of xy is a product distribution. And we have this exponential decay that's like the classical case. We also have from Düner, Storer, and Wittig, that also for projection games, we also have a quantum parallel repetition theorem. So our main result that we prove is we focus also on the case of free games, so product input distribution. And we prove that the entangled value of this repeated game decays like 1 minus epsilon to the 3 halves raised to the power n over s, where s is the length of Alice and Bob's answers. Okay, so how is this a result? Well, it's a better upper bound on the repeated game value than what was known previously. And so what's different here is that the power on epsilon is different. It's better. We save a factor of square root epsilon. Okay, and this is the bound that was obtained by Jane et al. And Xiaoyu and Scarpa last year. Okay, so it's a better bound, but what's the big deal? We just went from a base of 1 minus epsilon squared to 1 minus epsilon to the 3 halves. What's to write home about? Well, I find this interesting for two reasons. And the first is we don't know of a classical analog. Okay, people have thought about parallel repetition not only in general, but in the case of free games. And perhaps the most interesting reason, I think, is our proof uses some new tools from quantum communication complexity. So let's talk about the classical case. In 2009, Boaz Barak, Anoop, Ron Raz, Ricky Rosen, Ronen Shaltiel proved this result. That's somewhat similar to ours, that for a free game G, the classical, players Alice and Bob who only use classical strategies, the decay and the entangled value is 1 minus epsilon squared raised to the n over s. Okay, is this tight? We don't really know, except we know that other types of games, this what Ron showed, for projection games, this squared, this 2 exponent is necessary. Okay, so it's plausible that this bound that of Barak et al. Is also tight. And if this is so, then this would indicate that there's some separation between how games behave, quantum games and classical games behave under parallel repetition. Okay. And so you can think of this as we've sort of obtained a quantum speedup of parallel repetition. So we've shown a better upper bound on the entangled value of this repeated game, and we show that it goes to 0 faster with the number of repetitions. And in order to get this quantum speedup, we leverage a pretty novel connection between communication complexity and parallel repetition that was introduced by Xiaoyu and Scarpa. So, historically, if you look at the proofs of, say, the classical parallel repetition theorem, there are a lot of commonalities between that and the way people prove communication lower bounds, like namely that of disjointness. But their connection, they use an explicit communication protocol in order to analyze this repeated game value. Okay. So in their paper, I'll describe how you use communication protocols to analyze parallel repetition. But I want to say that in their paper, they use a very basic communication protocol, okay? But it's good enough to obtain this bound. And in our work, we use a faster quantum communication protocol, okay? And because it's, not only is it because it's quantum, but it uses fewer bits of communication, is why we save on this epsilon, the exponent of epsilon. And basically, to give away the punchline, why is it fast? Well, we use a distributed version of the Grover search algorithm in this protocol. And what is that algorithm? Well, it says that you can search an unordered list of n items for some marked item in time square root n, okay? And it's this quadratic savings in search time that allows us to save this square root epsilon. Okay, and so I find this interesting for a bunch of reasons. It's a new technique for proving parallel repetition, maybe even more intuitive. And this is an example of a phenomenon of better upper bounds yielding better lower bounds in complexity theory. And and we over the last several decades, we've spent a lot of time building better and better communication protocols, making them faster, more robust, so on. And so we can hopefully draw upon that rich toolbox of techniques that people have worked on to prove these direct product and direct sum theorems. And I think it's somewhat timely because we have a motto, and these days a lot of people are announcing their run for presidency, and they're announcing campaign slogans. So if we were to run for office, this would be our campaign slogan: better parallel repetition theorems from better communication protocols. Okay, so how do communication protocols come into play? So let me walk you through a high-level proof outline of how you prove parallel repetition. So you start with a two-player game, G, and it has entangled value 1 minus epsilon. So the high-level proof idea is you take a two-good strategy S for this repeated game, and you convert it to a strategy T for the original game that does better than 1 minus epsilon, which would be a contradiction. And the most natural way to do this is if you get single game inputs X and Y, you embed them in some coordinate of this global strategy. You sort of pretend that you're playing this repeated game, and you insert your inputs into some coordinate I, conditioned on some event W, where if you play this strategy conditioned on this event W, the probability that you win this coordinate I is greater than 1 minus epsilon. So that's the high-level idea. But let me make it a little more precise. So let's let bold-faced letters indicate inputs and outputs for the repeated game. So let's say there's an optimal strategy for G to the n. And it's a quantum strategy, so Alice and Bob share some entanglement, and they make some measurements and so on. And let's say that the entangled value of this repeated game is 2 to the minus gamma n. And our goal is to show that this gamma is large. So we want to show that this entangled value looks like 2 to the minus n-ish. So the goal of this embedding stated in these terms, well, Alice and Bob, if they're given X and Y, they would like to simulate this repeated game strategy conditioned on xi being this little x and yi being little y, also conditioned on w, and they want to simulate this without any communication. So in general, is it possible to do this simulation without communication? not generally, but there are sufficient conditions for this to be possible. And these are the sufficient conditions that both Xiaoyun Scarpa and Jane et al. Came up with. And it's some mutual information conditions. And what are they intuitively saying? They say that, well, suppose you look at, Alice and Bob, they play the strategy S, and you condition on this event W. How much information does Bob's side of the entanglement, along with his inputs, have about some coordinate of xi, one of Alice's inputs? And vice versa, how much does Alice know, her entanglement, how much information does that know about yi, one of Bob's questions? And if these two quantities are small, then you can do the simulation with some small error. And they can do this without any communication. So we just have to prove that these mutual information quantities are small. And the way that Xiaoyu and Scarpa do it is, well, they give an efficient communication protocol to generate this system and also determine whether this event W happened. And since the communication protocol is efficient, in turn implies that the mutual information is small. Okay.
What are EV and EA?
Good. So EA represents Alice's part of the entanglement. So it's some quantum system, and we can use mutual information to measure how much knowledge it has about X.
Quantum state of the classical measurement.
Right. So this is as quantum states. So this is quantum mutual information. But
this is true just in the free case, or?
Right. So this, definitely you need the freeness condition, because otherwise Y will have some mutual information with Xi if Y or I and Xi are correlated. So yeah, this is what a big place where we need.
So this is where you use freeness.
Yeah, this is a big place where we use it. So what's the outline? Well, you start with a too good strategy S for this repeated game. And since it's too good, it implies the existence of an efficient communication protocol to determine whether this event W happened. And since it's efficient, you can use it to bound the mutual information. So the protocol goes as follows. Alice and Bob, they get their repeated inputs. They play the game. And they engage in some short conversation such that by the end, they want to be able to conclude with high confidence whether this event W happened. Okay. And if we can show that this communication is short, the mutual information is, and then this implies the information is small, by the sufficient conditions I just described, we have a very good strategy for the single game, because we can do the simulation. So, let me say what this event W is. So in Xiaoyu and Scarpa, it's the event that if we choose a random subset of rounds of games, call it C, and it's not too large, and then we look at, did they win in all these rounds in C? Okay, and if they won in all of them, then we say the event W happened. Okay, so if this subset is of a certain size, it's gamma n over epsilon, where gammas are related to our winning probability, then if you look at a random coordinate outside of C, then with very good probability, they will win this coordinate. Okay. So this event W satisfies what we need. Now we just have to show that there's a short communication protocol for figuring out whether W happened. So what's their communication protocol? It's pretty straightforward. So what Alice and Bob do is, in the beginning, they use shared randomness to pick this set C. And they also, using public randomness, choose what the inputs are to these game rounds. And then Alice will privately sample the rest of her inputs. Bob will privately sample the rest of his inputs. And they can do this because we're assuming that the game input distribution is product. They can do this independently. They then play this game strategy, which in general will only, they'll only win all the rounds with exponentially small probability. But no matter. Now they want to do this checking. So Alice will send all her answers that she obtained in the C rounds. And she sends them to Bob. And then Bob just checks. Okay. So that's the communication protocol. So what good does this do us? So what's the communication complexity? The only time they talked was in step 4. Alice sends C of her answers. So C times the answer length. So that's the communication complexity. And this gives us a bound on the mutual information. So we can imagine that before they've talked, before step 4, how much information does Bob's part of the entanglement have about any of Alice's inputs other than this publicly sampled XC? And it should be 0, because Alice sampled these inputs independently. So Bob has no information. So the only way that he could have acquired some information is through this communication, but we're assuming that it's small. And so the mutual information condition on W is at most, some constant times the number of bits that were sent in this communication protocol, and vice versa. And this holds even conditioned on this event. So you apply the normal chain rule, and this implies that if Q is small, then Bob's knowledge of some xi should be Q over n. And this is some quantity gamma s over epsilon. Okay? So what does that mean? By our sufficient conditions, that means that Alice and Bob can do this, embedding without communication with this amount of error. But this implies that we have a strategy that wins with 1 minus O of epsilon, and that's because how we chose this event W. And we subtract off the error due to the simulation. And we get a contradiction when this gamma is less than epsilon squared over the answer length. So this is how Xiaoyu and Scarpa prove this 1 minus epsilon squared bound. So we want to prove a better bound. So we want to get a contradiction when gamma is larger. So when gamma can go all the way up to epsilon to 3/2. But if you run it through this Xiaoyu-Scarpa protocol, the communication complexity would be too much. It'd be square root epsilon times n. So we can't argue that this mutual information is little. So our solution is to use this faster protocol, Grover search, like I mentioned. So you can think of it, what is their protocol doing? They're just searching for this round in the subset C where they might have lost, right? So, if you're restricting yourself to classical protocols, they have to exchange at least C bits of communication, right? Because that's how many rounds they want to check. But let's take advantage of Grover search, okay? So in Grover search, you have n items. You can find a marked one using square root n queries, and it succeeds with constant probability. And the idea is, well, instead of doing classical search, let's have Bob run Grover's algorithm to search for such a losing coordinate, if there exists one. And whenever Bob needs to know what the value of AJ is, this is Alice's answer in the jth round, Bob will just communicate with Alice and say, tell me what AJ is. And so the hope here is the number of time that Bob needs to query should be about square root C. So, that's the hope. But can we actually get the communication to that low? Not quite, because this Grover search only works with 2/3 probability. And we actually need something that has extremely small error, exponentially small error. But we can fix this with some amplification tricks. But the general idea is to use Grover search. So what's our communication protocol? It's essentially the same. So they use shared randomness to pick this subset C, but then they break it up into blocks of size 1 over epsilon. Okay, so constant size blocks. So Alice and Bob play their strategy, and now they want to do this check. So for each of the blocks, Bob will run Grover search on, this 1 over epsilon size block. But when you do that, the amount of communication he has to perform is 1 over square root epsilon. Okay, and he just does this for every block. And they just look for a losing coordinate. And if there's no losing coordinate, they accept. So, what's the difference here? Well, the communication complexity is the number of blocks times 1 over square root epsilon times its alphabet size. And the key point is now that the denominator here is this square root epsilon. It's a bigger denominator, so we've saved on the communication. And if you run it through, since we have less communication, we can prove a better upper bound on this, on our winning probability. So that's how we get 1 minus epsilon to the 3/2. And that's essentially the proof. Okay. How much time do I have?
Just a minute.
Minute? Okay, great. So there's some technical details. So we don't run Grover naively. We have to use something called the Aronson-Ambinus protocol, which is a protocol for disjointness. We have a couple of other results. We can extend our proof to handle multiple players, not just 2. And we also have results for parallel repetition of games where Alice and Bob produce quantum states as answers. And this might have some future applications to quantum PCP conjecture if we ever get there. And perhaps, in terms of open questions, the biggest question is, what's the right answer for free games? Classically, is the epsilon squared tight? Or can we do better? Or is there actually a quantum classical separation? Thank you. Questions for Henry?
Is there something that, these possibilities that you listed that you strongly believe would be the case?
Right. So somehow epsilon to the 3/2 doesn't seem like the right number. But on the other hand, classically, I don't know, I get the sense that epsilon squared is the right answer. I don't know. So I think there is a separation, but maybe quantumly you can get actually 1 minus epsilon.
You showed that the quantum value of the game can differ from the classical value. Is there any bound known of how high it can be, or can one of them be 1 and the other is less than 1?
Right. So we know of there's a huge separation when you measure it in terms of distance from 1/2. I can't think of the top of my head where 1 is close to 1 and the other is extremely close to 0. No.
There are examples. The quantum is 1, and the classical is a 6.
Oh, like the magic square game, I guess.
No, this is 3 players. With 2 players. When the quantum is 1,
Right.
the classical can be reduced to close to 0.
Oh, that's right. Yeah. Right. Yeah. More questions? Okay, let's thank Henry.